All right, file system, specifically review of the extended style file system. Now the first thing that I want to mention is just the general idea of what we're trying to do with a file system. A file system is kind of like a map, like a hash table or a tree map, where we're trying to map string keys to file values. And specifically, that looks like this. We're going to have our key, which is a path, and we're mapping that to a pair. And that pair is some file data and some file metadata. For example, we could decide that we want to map the path foo bar.text to the data, the string hello bar, and the metadata owner Bob, size 1, 2, 3, 4, 5, 6, 7, 8, 9 bytes, etc. That's sort of any way that we could find to represent that map would be sufficient to work as a file system. But using like the sort of obvious solutions of a hash table that just maps a string to this other stuff, or a like binary search tree, or even a B+ tree directly, isn't what people have done historically, because the situation with things like being able to recover from data corruption with a file system checker, and trying to optimize for not necessarily the properties of a spinning disk as far as avoiding seek times, but the properties of a spinning disk as far as having a large block size and wanting to reasonably efficiently pack data into blocks. As a result, we've gotten these sort of block-based file systems as the default for the way this is handled. So in the ext style file system specifically, and that's what you're going to want to do for the like straightforward part of the upcoming assignment, the general layout looks like this. We have sort of two layers of mapping. We have a path to inode mapping, and then we have an inode to data block mapping. And this is sort of looks like the inode to data block mapping is on the top of the thing. We have a path to inode mapping. And so these two mappings sort of make up what we're doing in the structure of the file system. And the sort of story here is that we have an extra layer of indirection compared to the simple map that we would have had otherwise, and the structure that we would have in something like a fat file system. And what this lets us do is specifically this allows us to implement hard links. And that is a feature that you're going to be building for the sort of basic file system functionality. And so you're going to need to implement something that has an ext style behavior, at least. It doesn't necessarily have to be the standard structure of an ext style file system. It just needs to be a file system that passes the tests and is somewhat reasonable. But an ext style file system is going to be the simplest way to do this, because in order to get hard links and make it so that you can have multiple paths that map to the same inode, but a single inode maps to data blocks, and therefore the paths that map to the same inode point to the same data blocks, to get that structure, an ext style file system is a reasonable way to do it. All right, so to do that, we have the following on-disk structure. On our disk, we've got a bunch of disk here, and the first thing that we have in the disk is a super block. Let's think for a moment about the sort of stuff that we need in the super block. This usually is storing sort of formatting metadata about the file system. So here in the super block, we have things like block size. We have root, directory, inode number. We have number of inodes. we have number of data blocks, etc. It's this sort of metadata that we pick at formatting time. And one thing that is an interesting observation about the file systems that we're going to be building is that everything that we normally store in a superblock, we can get away with making a constant. So in the starter code, block size is a constant. This is 4096 bytes. That's the page size. That's the most common block size for an ext style file system. So we don't bother storing it in the superblock because we're just going to make it a constant in our code. Similarly, in the starter code, we're going to go ahead and make the root directory inode number just be a constant. The root directory is always inode number 0. We don't use inode number 0 for anything else. We always use it for the root directory, and that's okay because we always need a root directory in our file system. So assigning an arbitrary inode number as the root directory works fine. Similarly, we're going to set the number of inodes fixed. I don't remember offhand what the number was in the starter code, but for the purpose of what I'm saying here, it doesn't really matter. This could be 64, and it's just going to be hard-coded in the starter code, or hard-coded in your file system, as long as you can get away with that. And that works. Similarly, number of data blocks. In the assignments that we're going to be doing, what's going on here is we have a fixed size disk for the upcoming assignment. We have a fixed size disk of size 1 megabyte. And that means that once we've figured out what our block size is and how many inodes we have and how much space the inodes and the data bitmaps are going to take up, this can end up being fixed as well. And if we just divide 4K into 1 meg, we get, think about this for a second, you should be able to get it before I get it, we get 256 blocks on our virtual 1 meg disk. And some of those blocks are going to get used for metadata. I don't know how big an inode is. You'd have to calculate how big the bitmaps are, but there are some number of pages at the beginning of the disk that are going to, or some number of blocks at the beginning of the disk that are going to be reserved for this metadata, and then the rest of them will be data blocks. So it turns out that we don't actually need a super block for our version of an ext file system for the homework. So I'm going to skip the super block. After the super block, the next thing that we have is bitmaps. We have two bitmaps. We have a inode bitmap, and we have a data block bitmap. And what these bitmaps do is they keep track of, for each inode and for each data block, whether that inode or data block is currently in use. If the corresponding bit in the bitmap is 1, then that inode or block is used. If it's 0, that inode or block is free, which means that if we're trying to allocate an inode to create a new file, or if we're trying to allocate a data block, either to add it to a new file or to add it to an existing file, then if we have a 0 bit in the bitmap, the corresponding bitmap, that means that's a place that we can put that stuff. That's a corresponding object that we can allocate. So these bitmaps, the inode bitmap has to be 1 bit per inode in our file system. So if you remember from our example, we had said we were going to do 64 inodes for this example. So that would mean that our inode bitmap is 64 bits, is 8 bytes. We probably don't need to spend an entire block on our inode bitmap. We might be able to share a block for both our inode bitmap and our data bitmap, especially since even if we just ignore this inode bitmap and metadata blocks entirely for a second, this is no more than 256 bits. And if we do some arithmetic here by staring at the 64 as 8, then 128 is going to be 16, so 256 is going to be 32. And so turns out that our bitmaps in this example are 40 bytes. So that crams nicely into the first block, block number 0. So block number 0 is going to be our bitmaps block, or maybe it'll be our metadata block. We might be able to fit our inodes in there too. Have to figure that out. But it's at least going to be our bitmap block. After our bitmaps, we have our inodes. Now, inodes store metadata about individual files or other file system objects. And we'll go ahead and see a couple of examples of what sort of metadata needs to be in there. But minimally, we need to have a list of data blocks. And we use this interesting mechanism for list of data blocks in the slides, where we have some fixed number of data blocks, and then if we fill up all the fixed data blocks that are directly in the inode, we're going to use indirect blocks, where we'll allocate an entire block just of block numbers, which point to additional data blocks. And for this design, probably we don't want to make it so that we're going to use an entire, so that we could store the maximum file size of 256 or 254 or whatever it is blocks by having an array that big in the data block, or sorry, in the inode, because then inodes would be huge. They would be, well, depending on how we optimize this, but we probably don't want to optimize completely for this sort of 1 meg thing, so we probably want to use more than 1 byte per block number. And so that means even if we use 16-bit block numbers, 256 would be 512 bytes. And then we could only have 4 inodes, which would mean that we could only have 4 files, at least if we wanted to have inodes all fit in 1 page. If we wanted to have inodes be in more pages, then maybe 4 inodes per page is okay, but that seems a little bit big. That prevents us from having very many files on our file system. We'd like to be able to have at least 10 or 20 files on our file system. So we want to have our inodes be smaller. So there's a trade-off of how many direct and indirect pointers we have. In the starter code, there aren't actually explicit direct pointers. We have this restriction that the number that every file can only be 1 data block. And that means that we can make this assumption that the data block number that's assigned to a file is the same as the inode number. And that is a convenient assumption, but that's one of the first things that you're going to want to change in the starter code. Is you're going to want to make it so that the inodes really contain an array of block numbers and maybe 1 or more indirect blocks. Actually, if we think about it for a second, a block can store, if we use 32-bit numbers, and there's no reason to use bigger than 32-bit numbers, a block can store 1024 block numbers. And so even 1 indirect block is going to be able to store more block numbers than we could possibly use in our 256 block file system. So no matter how many direct blocks we decide to use, if we even have 1 indirect block for this 1 meg file system, that will be plenty to store all the data blocks that we could possibly ever have in a file. So that's the rest of the disk here, is data blocks. So now if we're trying to find a file, the thing that we're doing is we're going to be taking a path and trying to map it to an inode. And the way we do that is we're going to figure out, we logically look at our super block, but we don't have to do that because we're using constants instead. At least in the starter code design, that's how it works. You might discover that you need some small amount of super block data. The bitmaps are only 40 bytes, so you can put your super block data in the same block as the bitmaps. But we know that our root directory, which is where we're going to start any directory traversal, is going to be inode number 0. So let me give an example of doing some tree traversals. So if we have a path within our file system, we're not worried about absolute paths on the host system. We're only worried about paths within our file system. So let me just be clear what I mean by that. So if our path on the machine is home nat homework 7 mount, and that's where we've mounted our file system. And then the file within the file system that we're looking for is work hello.text, then the part of this path that we're interested in for the purpose of implementing our file system is just the portion within our file system. So our fuse driver is going to get a path /work/hello.text. So we're going to ignore the mount point and the rest of the system for the purpose of this discussion. So we have a path like work hello.text, and what we want to do with that path is we want to translate it into an inode. But that's going to take a couple steps because we have to do some directory lookups. And what a directory is on an ext style file system is a map. And what it's going to map is a file name to a inode number. So given a single file name, not a path, but a file name, we're going to map that to an inode number. So we're going to start off by figuring out what the first portion of our path is. This slash here is talking about the root directory. We don't have to do any lookups to find the root directory. We know that's inode number 0. And so in order to then do our first lookup, we need to go get inode number 0, which is the root directory. We have to find its data blocks. We have to interpret the data in the data blocks as this map. And then we have to do a lookup there. Now the lookup that we're going to do is the first portion of this path, which is this name work. So inside the root directory, we have another object named work. We're going to go find it. So in the map that is the root directory, we're going to look up the name work, and that's going to give us another inode number. So this work directory, so root is inode 0, and I'm going to say that work is going to be inode number 1, just for the fun of it. So we look up work and we get inode number 1. Again, work in this case turns out to be a directory. So this isn't, we're not done. We need to do some more lookupping. But the next thing that we're going to look up is hello.text, and we're going to look up hello.text in the work directory. So we're going to go find inode 1, find the associated data blocks, interpret them as a map, and then we're going to look up the string hello.text in that map, get back a number, and we find out that /work/hello.text is going to be inode 2. And then whatever operations we're trying to do on hello.text, we can find the metadata for hello.text directly in inode 2, and we can find the data for hello.text in the data blocks that are referenced in inode 2. So that's how we're doing the translation of paths into inode numbers, is by this directory traversal process. The next question this raises is how do we actually store that data within a directory? And there's a bunch of ways to do that. We could like serialize a hash table in there or serialize a B tree in there. That's how modern file systems mostly do it. And yes, that could be the harder part of this file system sequence, could involve implementing a B tree to make directories more efficient. We'll see if we do that or not. But the simplest way to do this is to just have a table. So we can have a like struct dirent that's going to stand for directory entry. And what we're trying to do is we're trying to map strings to integers, to inode numbers. So we'll have a string in here, name, and to make this as simple as absolutely possible, we'll have it be a fixed length. And for this example, I'll make it a fixed length of 16. And then we'll have our int enum. And then we'll realize that this isn't actually that great because 16 plus 4 is 20. We can't fit an even number of size 20 objects into a block. So I'm going to make this be 28. Our maximum file name length is going to be 27 because we'll go ahead and have a null in here just so that we can use library functions like strcomp. But this is going to be our directory entry structure for this example. And then what a directory is going to be, we have an inode for the directory, and the inode's going to have a length in it. And we know that the size of a directory entry is 32 here, 28 plus 4. So to find out how many entries are in the directory, we're going to take the size, which is one of the fields in the inode. Normally size is in bytes. It doesn't necessarily have to be, but it's easiest if we make size be in bytes. So we'll divide that by 32 to find out how many directory entries there are. And then we can just go ahead and either in the starter code for the assignment, we're using mmap to load our disk image and therefore all of our disk blocks into memory. So once we have a pointer to a disk block, it's just a pointer and we can use it. We can cast it to something like an array of durants. But once we have the beginning of our directory data, we can treat it as an array of directory entries and then like loop through it to scan for the appropriate file name. And that's sort of the easiest way to implement a map or a map of like string to int is going to be to have a structure like this of fixed size, and then all of our map operations are just looping through the array. All right, so we know how to do a tree traversal. We know how to do a directory lookup. That's mostly the whole story. The only remaining trick is thinking a little bit about that inode. So in that inode, we're going to have some fields that we definitely want to have. Size, and I'm going to recommend that this is in bytes. Now, something that we can derive from our size field is how many blocks of data a file or directory is. Just divide by 4096, which is our block size, and that will give us the number of blocks. But we also need to have this in order to know within those blocks how much of those blocks are valid data, and then the stuff beyond the size of the file is just going to be junk, extra space. So if we have a file that's of size 100, then the first 100 bytes of its first data block are going to be valid, and then the remaining almost 4K of data in that data block is going to be junk. We're going to have our data blocks, and this is logically a list. And this is in order, so if our data blocks are 3, 7, then that means that the file has 2 data blocks, and data block 3 comes first, data block 7 is going to come second. The one other thing that we're going to need to have in here for the current homework is going to be ref count, which is going to keep track of how many hard links there are to this inode. And as we unlink directory entries, so you do an unlink, that's an operation on a directory entry, it's going to remove a directory entry, which is a mapping from a name to this inode. Every time you unlink, we'll decrease the reference count. And when reference count goes to 0, we can mark this inode as unused because there's no more references to it. I think that's most of the core idea on the ext file system. So I'm going to take a quick break and then we'll go walk through the concrete starter code.